All right, good morning, everyone. Welcome to Wednesday, 7 a.m. Lab for Advanced Instrumentation. This week we're going to be talking about range of motion. I think you guys in clinic maybe doing some range of motion, but you have these handheld inclinometers, which you put on the patient. And the problem with that is trying to hold them on as the patient's moving around, and there could be some slippage issues, so you may not get the most accurate result. So the equipment we use in lab, which is the CLA Insight, allows you to strap the inclinometers onto the people's head and back so that when you do range of motion through the Bluetooth technology, the wireless technology, you can get the digital range of motion reading, and it tends to be more accurate. You don't have to worry about the slippage because it's Velcroed on. Now, hopefully you guys did your assignment and watched the video on range of motion under lab videos. If you have not, then go ahead and watch it. It just shows me going through and doing a range of motion with this equipment, so you kind of have an idea of what it looks like. When we do it in lab, students really like it. They prefer it to the handheld version. And if you want to experience it yourself, when you do get back on campus, in unit 7 of the clinic, they have one of these units. So go ahead and try it out for yourself. All right, since we don't have equipment, online, what we're going to do is spend the rest of the class talking about why you'd want to look at someone's range of motion. How does that help us know what's going on with the nervous system, and what to do with the results when we get them. So first of all, in and around joints, there are receptors called proprioceptors, right? Proprioceptors. So these proprioceptors, I don't know, can you guys see my board here okay? You see that? Can you give me like one of these, one of these? Yeah, okay. These proprioceptors are muscle spindle cells, Golgi tendon organs, and joint mechanoreceptors. So all these kind of proprioceptors send to the brain the information of where my body is in space. So I know where my arm is, I know where my leg is, I know where my neck is, and that's really important because if I want to do anything, if I want to move and do anything, let's say I was trying to reach this marker here, I have to create a motor plan to grab it. Now that motor plan will be entirely different if my arm is up here, it's got to come down, or if my arm is starting out here, it's got to come up to it. So in order to have smooth, accurate movement, I have to know where I am in space. So let's talk about that just a little bit. I have this handout that we could go over quickly. Let me pull that up for you. In lab, I typically hand this out and you guys get in your little groups and you go over it. But there's just a few of us here, so we might as well just do it together. So I'm going to ask you questions. Please respond, either say it or type it in chat. So if patients have decreased range of motion or just any kind of aberrant range of motion, what do you think anatomically or structurally happens at the joints, over time? This is your part to either talk or type. What do you think? What happens to those joints when range of motion isn't normal? Yeah, so we get adhesions, which make the joints work even worse. And the reason those adhesions build up is because the joints become unstable, right? And that instability can cause destruction of cartilage in and around joints, like bony spurs, changes in the bone growth. And that instability causes the body to contract the muscles around the joint to stabilize it, or what we call splint the joint. Now, when you think about a spinal cord, like a vertebral column. And if one vertebral joint gets splinted and immobilized, what happens to the function of the joint above and below it? Does it increase in motion? Does it stay the same? Does it decrease in motion? So eventually it will, but initially, Devin, in compensation of a non-moving joint, the joints actually increase their range of motion. So this increased range of motion above and below a splinted joint will cause degeneration of the joint, because hypermobility degenerates joints too. So after those start to degenerate, they will become splinted, and so on and so on and so on. And that's how having bad range of motion in a joint can actually, over time, spread up or down the cord, on the vertebral column, because as one joint tries to take over for the other, and then it starts to degenerate. So it's really bad to have range of motion difficulties in your joints, and that's what we want to do something about it. Let's pop down to number 2 and talk about the motor consequences of having range of motion restrictions. What kind of functional issues do you think patients come in complaining of when they can't move their joints normally? What brings them into your office? What do you think? People can't move as well. What would that affect in their lives? What would they complain of? Okay, the motor signal wants to perform a movement and task the joint can't perform. The motor signals can also be interfered with. Pain. Okay, so all these things are true. Pain is definitely something that people are going to come in with when joints start to deteriorate. That can fire those nociceptors, causing pain. Yeah, they're unable to do their activities of daily living. Very good. So all the things that they like to do in a day, they now can't do. So I would say most patients would come into my practice because of pain, discomfort, but there's also a good amount that they'll deal with pain. They don't really care about pain, but when now they can't do the things that they want to do, like play tennis or play golf or drive because they can't turn their head, that drives them into your office too. So when they have functional limitations and they can't move well, as I was telling you before, if I can't create a motor plan because I don't know where I am in space, then my movement becomes jerky. You've heard of the term dysmetria, right? Dys meaning bad, metria being measurement. I can't measure where I need to go because I'm not getting good sensory input. Which brings us to number 3. What consequences would it have on the sensory nervous system? A lot of people think, oh, well, I have decreased range of motion, I can't move so well. It's a motor problem. Well, it's also actually a pretty bad sensory issue because of all the proprioceptors that I just talked about. When I can't move a joint properly, that affects proper proprioception, which is a problem for 2 different reasons. One, we just spoke about, where I can't create good motor plans because I don't have good information about where I am in space. But 2, and arguably most importantly, this proprioception goes up to the brain and fires and stimulates the neurons in the brain all the time because we're always in a gravitational environment. Proprioception is the number 1 component to stimulation of the neurons in the brain. Because as you may be aware, the neurons in the brain need stimulation to stay alive. Remember, they need activation as well as oxygenation and nutrition, right? So the number one component is stimulation from the proprioceptors. So if we have bad range of motion, then we're not getting the normal stimulation up into the brain that is necessary for those neurons to stay alive. And what's really interesting is the number one area of the body that stimulation comes through for proprioception is around the spine. That's what we work with. And the number one area, the most stimulation in the spine, comes from the atlas area, which gives a lot of credibility to these upper cervical techniques, right? Because the most sensory proprioceptive stimulation comes from that atlas area. There's a very rich bed of receptors there. So we want to make sure the patients always have good range of motion so that they get normal proprioceptive information and stimulation so that the body can function normally. Because if these areas of the brain and the brainstem aren't getting their normal and appropriate stimulation, then it doesn't make sense that they would be able to work as well either. And we know that the brain controls all the different functions of our body. So people could have far-reaching repercussions due to decreased range of motion and subluxation. Any questions with that so far? You guys are stunned in silence, I can tell. All right, well, we will continue. So let's talk about the two different nervous system tracts that bring this information up into the brain so we understand what will be affected with subluxations and decreased range of motion. So I already have it drawn out for you, so you can just follow along. The two tracts that carry proprioception are the dorsal columns and the spinal cerebellar tract. The dorsal columns carries conscious proprioception along with light touch and 2-point discrimination, those sort of things. And what happens is when you have a joint, and that is supposed to be a drawing of an elbow, the peripheral nerve will carry it into the spine. Oh yeah, just to orient you, here's an elbow, here's an ankle, here's a spine, here's the brainstem, here's the cerebellum. I've kind of split it in half there. You know, there's one cerebellum, but it's behind the brainstem, which is very difficult to draw in 2D. So I've just kind of drawn the left and right side there, but it is just one cerebellum in the back. And then up here is the cortex, that outer area of your brain, where you have the 4 lobes. And I just wrote F for frontal and P for parietal, which are 2 of the lobes up there. All right. So we have proprioception coming in from, the limbs or from, the side of the body, whatever, going into the cord. And here what I've done is I've transected the cord and drawn here. So here's the back, here's the front. Here is the dorsal columns, right in the back of the cord, right? Dorsal column, so it's in the dorsal part or the back part. Now, if you recall, there are 2 different tracts that go up in the dorsal columns. There's the fasciculus gracilis and the fasciculus cuneatus. And there's 2 of each because there's a left and a right side. So we have the fasciculus gracilis. They come up most medially, right up the center. Fasciculus gracilis brings information from the feet. You can remember that because the feet stand on grass, right? So fasciculus gracilis brings us the information from the feet, which leaves the 2 tracts on the outside, fasciculus cuneatus, which brings in the information from the arms, okay? And that's important to know because if I have, let's say, a patient and they come in and they've lost proprioception from both of their feet, I could think, well, I wonder if there's just one lesion in the spinal cord that's causing them to lose proprioception in the feet. But their hands have been spared. There's nothing wrong with their hands. And as you can see, because these two gracilis fasciculi are together, I could have one lesion that would affect both of them, but it may not be big enough to affect the hands. Now, over time, that lesion could grow so that at first the feet are affected, but not the hands, but eventually now the hands are affected as well. All right. So the proprioception comes in. I'm using red for dorsal columns. Dorsal columns will ascend up. From the arm will be the fasciculus cuneatus. It'll go up the spine, and it crosses over in the very lowest part of the medulla, that lowest part of the brainstem. Then it ascends up through the brainstem and ultimately to that sensory lobe in the cortex, which is the parietal lobe. So that means to say, if we have range of motion difficulties on one side of the body, and I'm making this the right side because I like to make it as if you're looking at a patient, right? Because that's how you're normally going to be oriented. This would be the patient's right side. Proprioception and range of motion difficulties on one side affect the contralateral brain, okay? Contralateral brainstem and brain because of dorsal columns. Any questions with that? Nope. Okay. Let's go on to spinal cerebellar. As the name would imply, it goes from the spine to the cerebellum, and there's two tracks. There's a dorsal track in the back and a ventral track up front. And I've drawn them over here for you in my little transected spine. Here's the dorsal spinal cerebellar tract. Here's the ventral spinal cerebellar tract. So here's how it works. And again, these are the basics of the tracks. It's a little more involved than this, but I just want to give you the basics. From, again, let's say the elbow, unconscious perception is being carried through the spinal cerebellar tract. So it's going through the peripheral nerve to the cord. Once it gets to the cord, spinal cerebellar is in green in my drawing. From the arm, it's going to come in and it's going to ascend through the dorsal spinal cerebellar tract. It's like a fast track right up, same side. So same side arm, same side cerebellum. So it just goes straight up. The green goes straight up through to the medulla and then right to the cerebellum. Now, when you talk about the legs and the feet, the lower body, that uses the ventral spinal cerebellar tract. Now that's a little more complicated. What that does, in from the legs, comes into the spine. Now it crosses over to the contralateral side of the spine at that level and ascends in the ventral tract, in the front one. That goes all the way up to the midbrain and into the contralateral cerebellum. So it goes to the other cerebellum, but it doesn't stay there. That information and that stimulation goes from the contralateral cerebellum back to the ipsilateral side of the cerebellum. Remember, there's one cerebellum. I'm just talking about the different sides. I have a dotted line here because it actually doesn't go through the midbrain. It just goes from one side of the cerebellum to the other, behind the brainstem. So I just had a little dotted line, meaning it's happening behind this. So ultimately, what's happening is range of motion, proprioception that affects one side of the body will ultimately affect the ipsilateral cerebellum. That's why I have ultimately ipsilateral on here. Yeah, from the lower lip, it also does affect the contralateral cerebellum, but that also comes back to the ipsilateral one. So when you have restrictions, range of motion, when you have subluxations, you have to think about what is going on neurologically. So in the spine, you want to be concerned about the ipsilateral cerebellar function. You want to be concerned about the contralateral and brain. Because if these range of motions are restrictions are chronic, if the subluxations are chronic, then we know for a long time these areas haven't been getting normal stimulation, which means the function of the neurons in them could be compromised. if the function of the neurons are compromised, then whatever it controls could therefore be compromised. So we want to do a good history and figure out, are they having other issues like, I don't know, digestion or elimination or heart or lung or, what have you, because perhaps these areas of the brain and brainstem that haven't been getting their normal stimulation aren't firing down and doing their activities as well. Does that make sense? You guys all look so excited about this information. You're like, it's early talk. I know. But listen, I like sharing this with you because this is the crux of what we do, right? This is what we do in chiropractic. We fire proprioceptors and we change function in the nervous system. And this is how it works. Because when a patient comes in and they have these subluxations, let's say, so they have aberrant range of motion, and we know the areas that could be compromised, what do we do? Well, number one, I would test these areas of the brain and brainstem to see if we do have compromise, number one. And when you take my Intro to Functional Neurology class, I'm going to teach you how to do all that. There's my blatant plug for the week. But you guys know some of it, like you know how to do alternating hands up down for cerebellar function. You can do finger tapping, which is fine motor function for the contralateral cortex. You could do sensory testing for contralateral parietal lobe function. So basically you just see, are those areas working or not? And let's say we did have some compromise. Let's say we had a problem with the finger tapping test, which tells us that that contralateral frontal lobe isn't working well. Well, what do? I have subluxations on the right. My frontal lobe on the left is doing well. Well, there is a really good fix that we all know about. We can do an adjustment. And look what happens. If we go ahead and adjust this side of the body, the side that has these range of motion restrictions, these subluxations, then that stimulation will go up the same tracks. We're firing the same proprioceptors, causing stimulation up the same tracks that are going to the same neurological areas like parietal lobe, cerebellum, brainstem, all that, causing increase in stimulation to all these areas. So if previously they had decreased function due to decreased stimulation, we're providing the stimulation. We're helping those neurons work better. And so the hope is, right, that with greater stimulation, we will get improved and optimal and normalized neuronal function, which will therefore fire back down and cause normal function in the body and in around the joint. Because remember, when you adjust a joint, it's not that we're just putting a bone back in place. Like that's kind of the thought, that's sort of what you're taught initially to kind of get an idea of it. But what's really happening is you're firing proprioceptors that go into the nervous system that send back signals to contract muscles differently to help hold the bone in its proper place, in the proper juxtaposition, right? It's kind of what's happening. So this is what's really cool about understanding the neurology, is you can start to understand why we get such great results with adjustments in chiropractic, because you see how that's working. Cool stuff, huh? So any questions on any of that? Because that's pretty much my little spiel on range of motion. You guys are quiet as church mice this morning. Joshua gives me a thumbs up. Jasmine says thank you. All right. Well, if a question bubbles up, let me know. I'm just going to give you a little bit of a heads up about what's coming up this week and next week. So this week is week 3. The only thing left for you guys to do is to make sure that you take the range of motion lab quiz, which is due 11:59 Sunday evening. Next week, we're going to be talking about a really cool subject called QEEG, quantitative electroencephalography. Hopefully you received my email yesterday with the steps about what you need to do in preparation for lecture and lab next week. Now, QEEG is where we put electrodes on people's heads and we actually read brain waves. It's pretty cool stuff. We donated a bunch of this equipment by a company called BrainCore. BrainCore was created and is run by 3 alumni of Life University, 3 chiropractors that have used it in their clinic and seen really great information and results from patients using the information they attained from it. So they've shared it with us. They have a website. I think it was braincoremembers.com. And if you go and register on it, then you'll be able to watch some of the videos that they've created for us. Now, you need to register at least 24 hours before you want to go in and watch videos, because it can take up to 24 hours for them to process your registration. So once they do, they're going to send you back an email, tell you that you're registered, and then you can go in and watch the videos. In the email and in announcements and in week-by-week instructions, all these areas, I have given you the instructions on how to do it. So hopefully you got it somewhere, right? If you have any questions, of course, call me, but usually it's pretty easy. You just register, go online, watch the video. And it's really important for you guys to watch the video for next week, because I want to talk about brain waves and how we're assessing them through QEEG. And I really need you to have sort of a picture in your mind of how this works before we talk about it. All right, so that is your assignment for this week. Any questions on that? You can give me, nope? You good? All right, there you go. That's it for this week. Have a wonderful week, guys. Take care. See you next week. Bye-bye.